At 8:41 a.m. on November 26, 1943, contrails twisted white scars across the frozen sky over Bremen. 12 F-190s of JG-11 rolled from altitude in disciplined silence, throttles open, guns armed. Below them, a column of silver aircraft clawed through the haze, Republic P-47 Thunderbolts from the 56th Fighter Group escorting B-17s home from another raid on the Ruhr. The Luftwaffe pilots expected easy kills. The Thunderbolt was a brute by reputation. 7 tons of steel and armor around a radial engine that should have made it sluggish. German intelligence files described it as a bomber that tries to fight. Most pilots of JG-26 and JG-11 had watched these machines crawl behind Mustangs and Lightnings and assumed their turning radius and climb rates were fatal limitations. Today, one Luftwaffe ace would learn what 2,800 horsepower really meant. Oberleutnant Heinrich Staller dived first, banking through 14,000 FT, 4,270 meters, and lining his gun sight on a Thunderbolt climbing to cover the formation's rear arc. He closed from 800 Wauwels D, 730 Mallorum, expecting the American fighter to roll away and climb too slowly to escape. Instead, the P-47 leveled, held its line for a heartbeat, and then did the impossible. It accelerated straight upward. The R-2800 Double Wasp in its nose hit full military power. Prop blades flattened into a shallow bite. Manifold pressure climbed past 52 nhg, 176 kPa, and a roar like a bursting boiler filled the sky. The Thunderbolt shot up through the attack path at 480 million per 772 km/h. Staller pulled hard to follow and watched the American fighter disappear above him, climbing as no radial-engined aircraft had ever climbed in combat. He shoved the throttle to the stop, but his BMW 801D could not keep up. Witnesses later estimated the Thunderbolt's dive-to-climb transition covered 3,000 FT 915 MEM in under 6 seconds. For Luftwaffe pilots accustomed to dictating vertical maneuvers, it was a reversal of physics. That 2,800 horsepower engine, weighing over a ton alone, had turned the heaviest fighter in the sky into a predator that could outrun its own dive. Below, the rest of the German formation committed. 4 attacked from 3 o'clock, others from above the bomber stream. The Thunderbolts broke apart in pairs, their dives controlled and deliberate. At 20,000 FT 660-100 downward M, the air grew thin and compressibility became a threat to any aircraft descending past 480 mph. Most fighters of the era lost control beyond that limit. The P-47 was built for it. Test data from Wright Field showed that the Thunderbolt's dive speed could exceed 500 mph, 805 km/h, before control surfaces locked. Its skin was stressed for 9G. No fighter in the European sky could match that margin. German pilots who tried to follow in a dive found their airspeed indicators flickering into red and their control sticks frozen by compressibility buffet. The Thunderbolt simply pulled away. Staller recovered his aircraft at 10,000 FT, 3,050 Mellor, and looked up through his canopy. He saw the same silver fighter coming down again, its 8 50-caliber guns flickering like a welding torch. Tracer lines walked across his wing route. 2 rounds hit the engine cowling. Black smoke filled his cockpit. He bailed out at 8,000 FT, 2,440 mil. It was over in 10 seconds. The rest of JG-11 broke contact. Their radio logs, captured later by Allied intelligence, recorded a phrase repeated 3 times. Donnerbolzen steigt wie ein Teufel. The Thunderbolt climbs like a devil. It was the first time Luftwaffe pilots realized that American radial engines had closed the performance gap with Germany's liquid-cooled fighters. The day's mission cost the 56th Group 1 bomber and no escorts. 5 German fighters were confirmed destroyed. The Thunderbolt's radios crackled with calls of returning formations. Fuel stayed low, but morale impossibly high. For pilots who'd entered combat flying what they'd been told was a flying tank, the sky felt different now. Their machine had become a hunter. Back at Boxted, Captain Francis Gabreski climbed from his cockpit and wrote a single line in his debrief log. Engine never quit. Could run from anything and catch anything else. He was recording performance data, not emotion, but the sentence captured the transformation of an entire air war. For the Luftwaffe, the lesson was shocking. For the Army Air Forces, it was vindication of a design philosophy that had looked absurd on paper. A 7-ton fighter that could dive like a falcon and climb like a racing aircraft. At its heart was one engine so powerful and so temperamental that even its builders had once called it impossible. The story of how that engine came to exist began a year earlier, inside a factory in East Hartford, Connecticut, where engineers faced mathematics that said a 2,000-horsepower radial could never cool itself in combat flight. They built it anyway. The Thunderbolt's triumph over Bremen had begun with failure. A decade of American engine design that lagged behind German precision until one company decided to redefine what a fighter engine could endure. In 1942, American fighters were still losing the war of climb and range. Every technical report from Europe said the same thing. The Luftwaffe's aircraft were faster to altitude, longer on station, and more precise in attack. The Allies could replace pilots and airframes. They could not replace physics. The British Merlin engine in the Spitfire delivered 1,300 horsepower on a good day. Germany's Daimler-Benz DB601 pushed 1,350 at altitude with direct fuel injection and superior climb efficiency. The later DB605 and Jumo 213 were even worse news for the Allies. Powerful, reliable, and designed for sustained high-boost operation without detonation. When American engineers studied captured German engines in 1943, they found something they had never achieved. Liquid-cooled precision, built like a Swiss watch, balanced to the tenth of a gram. By comparison, American airframes still flew behind their own technology. The Curtiss P-40 was rugged but underpowered. The P-39 Airacobra was unusable above $4,500 in Meru, where its single-stage supercharger choked. The early P-38 Lightnings overheated and vibrated to pieces in extended climbs. Every failure traced to the same root, engines that could not sustain combat power without boiling, pinging, or tearing themselves apart. The War Department called for a new fighter capable of maintaining 2,000 horsepower beyond 7,600 millimeters, 25,000 FT, and surviving 5 hours of flight at cruise. The requirement was mathematical nonsense. A radial engine that powerful would produce so much heat that its cylinders would fuse or its pistons would shatter under detonation. Liquid-cooled inline engines handled that problem with glycol and pressure systems. Radials had only airflow and hope. The Army Air Forces could not wait for a miracle. Every month of 1942, Allied bomber losses rose. From Schweinfurt to Regensburg, missions ended, with half their aircraft missing. Fighter escorts could not reach targets deep inside Germany. A new aircraft was needed, one with the speed of a Spitfire, the range of a Lightning, and the ruggedness of a bomber. No existing engine could deliver that. In July 1940, Republic aviation engineer Alexander Kartveli stood before a board of officers and drew a circle around the problem. If you wanted an aircraft to climb and dive like a fighter, but survive hits like a bomber, he said, the solution was not a smaller airframe. It was a stronger engine. And there was only one company in America trying to build an engine that outrageous, Pratt & Whitney. At the time, Pratt's engineers were still recovering from the failure of their R-2800 Twin Hornet. The Double Wasp project that replaced it was a gamble in every dimension. 18 cylinders in 2 rows, 2,000 out of 4 cubic inches, 45.9 liters, of displacement, and target power of 2,000 horsepower at takeoff. To some engineers, it looked less like a design proposal than a detonation experiment. Pratt's chief designer, Leon Gray, admitted in a 1941 memorandum, "If it runs for 5 hours at rated power, we will have changed the definition of reliability." Early bench tests burned through piston rings in 40 minutes. Supercharger temperatures reached 300 degrees. Cylinder heads warped until valves jammed. Oil foamed under centrifugal pressure and starved rear bearings. A single backfire at 2,000 RPM was enough to crack the induction manifold. Across the Atlantic, the Luftwaffe had already standardized its power plants. The BMW 801 and Daimler-Benz 605 families shared common parts and interchangeable accessories. German engine plants operated like clockwork factories. Pratt & Whitney operated like a laboratory fire. Each engine was hand-built and hand-modified, with every failure recorded in pencil on oil-stained test charts. The War Production Board worried about the cost. The Air Corps worried about weight. But Cardvelli and his team saw something no bureaucrat did. A radial engine did not need to be beautiful. It needed to be indestructible. If the R-2800 could deliver 2,000 horsepower, without liquid cooling, it would be immune to the bullet leaks that killed every inline fighter in the field. The first prototype flew in May 1940 on a Vought XF4U Corsair. The engine barely held together for 30 minutes, but the data was clear. Raw power was possible. What was missing was control. The supercharger lagged at altitude. Fuel mixture oscillations caused detonation at boost pressures above 46 nhg. Pratt engineers needed mathematics that did not yet exist. Compressor map analysis by hand, slide rule calculations for pressure ratios that even the Massachusetts Institute of Technology had never taught. In the meantime, Allied engineers tried to copy German methods. They failed for one reason. American engines had to run on American fuel. German fighters burned 96-octane C3 blend. Britain used 100 octane from synthetic sources. The United States had millions of barrels of $100, 130 aviation fuel from ethyl additives, chemically different, volatile, and hotter. That fuel demanded an engine strong enough to absorb abuse. The R-2800 was about to become that engine, but first it would nearly kill its own test pilots. The early Republic XP-47B was a monster in search of a power plant, a fuselage designed around the engine before the engine had proven itself. Ground tests in late 1941 recorded manifold pressures that made technicians run for cover when the throttle opened. Pilots complained that the turbo supercharger behind the cockpit sounded like a train boiler ready to explode. In one flight, the turbo inlet duct overpressurized and blew a panel off the rear fuselage. Yet when the XP-47B stayed together, it reached 637 km/h, 396 mep, on its second test flight, an impossible number for a radial fighter in 1941. Cardvelli knew then that if they could keep it cool and stable, the Thunderbolt would change everything. But the problem remained fundamental. How to tame 2,000 horsepower in an engine that wanted to tear itself apart. The solution would come from a series of explosions in a Connecticut test cell that no one was supposed to survive. In the winter of 1941, Pratt & Whitney's engineers rolled a prototype onto test stand number 2. Fired it at full boost for 7 hours, and watched temperature needles bury themselves against their stops. When the smoke cleared, the engine was still running. So was the idea that a radial could power a fighter past 500 mm. Inside the Pratt & Whitney plant at East Hartford, the Double Wasp was a contradiction built in metal. 18 cylinders, twin rows, 2 ignition plugs per cylinder, and a crankcase heavy enough to survive a collision. At full power, it inhaled 1 cubic meter of air every second and converted 380 liters of high-octane fuel per hour into heat that could melt pistons in minutes. Keeping that violence alive long enough to call it an engine required an industrial miracle. By late 1941, failure was routine. Cylinder number 7 detonated so violently during one test that fragments embedded in the concrete wall. Oil foamed under acceleration, turning to vapor that starved bearings. The twin-row configuration created a thermal trap. The rear cylinders cooked while the front cooled too much. Each test ended with the same report: power acceptable, cooling impossible. Pratt's engineers responded with mathematics and stubbornness. Chief metallurgist Elwood Pete Whitney introduced sodium-cooled exhaust valves borrowed from racing engines. Heat transfer increased 22%. Lubrication specialists redesigned oil baffles to force flow across the hottest bearing shells. A new 12-fin cylinder head, machined from forged aluminum, reduced temperature spread by 40 degrees Celsius. Each improvement solved one symptom and revealed another. The decisive change came from supercharging. To push air into the cylinders at altitude, engineers needed a two-stage, two-speed centrifugal compressor, an idea already used on Rolls-Royce Merlins, but far more dangerous on a radial. When the compressor overspun, it tore blades from its impeller at 40,000 RPM. When it lagged, combustion died. Finding balance meant redesigning every duct and intercooler by hand. Test stand number 2 became legend. On January 17, 1942, engineers ran an R-2800 for 335 minutes at 2,000 horsepower, then advanced throttle until manifold pressure reached 52 nhg. The temperature gauges maxed out. Coolant oil climbed past 127-degree quacks. Technicians hid behind concrete barriers. At the 5-hour mark, the throttle lever jammed from heat expansion. When they finally cut fuel, the engine coasted to silence, intact. The data log read simply, sustained power, stable temperatures, negligible wear. It was the first time a radial engine had survived full rated output for its entire service interval. Wright field inspectors arrived 2 weeks later to witness the repeat test. They verified specific fuel consumption of 0.46 lb per horsepower hour, a record for any air-cooled design. Power output reached 2,100 horsepower at sea level, 1,800 at 7,600 mm, 25,000 ft, using the new two-stage compressor. The R-2800 had become the most powerful, reliable engine in the world. What made it different was not brute force, but tolerance. Each piston ring was gas-hardened to survive 20 hours at detonation threshold. Cylinder heads were threaded, not bolted, allowing microscopic expansion without leakage. Fuel control relied on an automatic mixture unit that compensated for both altitude and temperature, the first American system to match German mechanical injection in precision. And because it was radial, it could take hits that would kill a liquid-cooled inline in seconds. A single bullet through a radiator ended a Daimler-Benz. A single bullet through an R-2800 cylinder barely changed manifold pressure. The Army Air Forces still doubted it. They wanted numbers. In March 1942, Pratt shipped an engine to the Bureau of Standards for destructive testing. It ran at 2,700 RPM for 8 hours before engineers cut power to inspect wear. None found. So they restarted it, without oil, and timed the result. The Double Wasp ran 2 minutes and 40 seconds dry before seizing. The test officer's report contained one sentence: recommend immediate production. At full combat rating, the R-2800 generated torque that twisted propeller shafts like licorice. To absorb it, Hamilton Standard built a new 3.7 MIP 12 FT2 in, hydromatic propeller with constant speed control. Its counterweights weighed more than entire early war engines. When Kartveli mated that propeller to the XP-47's prototype fuselage, the aircraft became the heaviest single-engine fighter ever flown. Most pilots thought it a death trap. Then they flew it. The first production, Thunderbolt, P-47B number 41-5905, reached 665 km/h, 413 mph in level flight at 7,600 hours. At $12,000 a minute with turbo supercharger engaged, speed touched 700 km/h. No other piston fighter on Earth could dive faster or climb higher without tearing apart. The numbers were unambiguous. A 2,004 cubic inch monster had made American air power competitive again. But the machine was barely controllable. The cockpit cooked above 38 degrees in climb. Pilots reported oxygen starvation when the turbo ducting overheated. Control cables ran the length of the fuselage beside a turbine that glowed orange. One test pilot compared it to sitting on a blast furnace and hoping the bolts hold. Republic engineers took notes, strengthened fittings, and accepted the heat as the price of supremacy. By summer 1942, Pratt & Whitney could finally deliver engines faster than Republic could build airframes. Each unit cost $27,500, half the price of an entire Spitfire MKV. Yet demand was endless. The Navy ordered them for F-6F Hellcats and F-4U Corsairs. Martin wanted them for B-26 Marauders. War Production Board forecasts predicted 125,000 units by 1945. The engine that had almost burned itself to ash now powered every decisive American aircraft in the war. For pilots, the difference between theory and survival would be tested over France. A 7-ton fighter built around an engine that refused to quit was about to meet an enemy that still believed radials couldn't win a duel. In April 1943, the first P-47s crossed the English Channel under their own power. German radar operators logged them as heavy bombers. They were about to learn the distinction firsthand. In the spring of 1943, the first production P-47Cs of the 56th Fighter Group taxied onto the steel-planked runway at King's Cliff. Pilots called them monsters, 7,900 kilograms of steel, armor, and turbine ducting. The aircraft's nose was a circle of propeller blades wider than a man was tall, and its fuselage hid a turbocharger system that made even maintenance crews nervous. But when the engine started, everything else on the airfield stopped moving. The sound of the R-2800 was not a roar, but a concussion. The turbocharger behind the cockpit spun at 21,000 RPM. The entire aircraft trembled as pressure surged through the ducts. When throttled forward, the Thunderbolt accelerated down the runway like a loaded truck pushed by a hurricane. No pilot had flown anything this heavy, that climbed this hard. Alexander Kartveli had designed the P-47 from the engine outward. Not a graceful airframe fitted to power, but a power plant with wings. He placed the cockpit high, moved the turbocharger aft to balance weight, and wrapped everything in armor plating thicker than any single-seat fighter in history. The result was a machine that looked blunt, almost clumsy, yet could dive at 800 km/h without losing control. In April, Colonel Hubert Zemke took command of the 56th. He'd flown P-40s in North Africa and expected the Thunderbolt to be another compromise. His first flight erased that doubt. At 7,600 m, 25,000 ft, the turbo engaged, and manifold pressure climbed to 52 in HH. The airspeed indicator passed 700 km/h. The cockpit shook but held. Zemke returned to base and told his group, "We've been given the heaviest fighter on Earth. It's our job to make it dance." Training revealed the contradiction at the heart of the P-47. Below 3,000 RPM, it handled like a bus. Its turn radius was double that of a Spitfire. But above 6,000 RPM, where turbo pressure restored full power, it became something else, stable, fast, and nearly indestructible. Pilots who learned to fight vertically diving through attacks instead of turning flat, discovered that the Thunderbolt could kill anything it could catch. In May, the 4th and 78th Fighter Groups joined Zemke's 56th in England. Together, they formed the backbone of 8th Fighter Command. Their mission was escort, shepherding daylight bomber streams into occupied Europe and home again. No one expected them to succeed. The Luftwaffe had ruled that airspace since 1939. The first Thunderbolt combat occurred on March 10, 1943, over Rouen. Lieutenant Paul Baer shot down an F-47 at $7,000 Thunderbolt using the new aircraft's exceptional dive speed to escape counterattack. 2 weeks later, Zemke's group engaged Bf-109s over the Netherlands. The Germans tried their standard tactic: climb, roll, and dive through the formation. The P-47s simply followed them down and kept diving. One German pilot radioed afterward that the American fighter fell like a stone but never broke apart. Ground crews learned their own lessons. Every flight returned with engine cowlings, blistered from heat. The turbocharger's ducts glowed cherry red during combat climbs. Mechanics joked that they worked on a flying foundry. Yet the engines kept running. Unlike liquid-cooled Mustangs, the Thunderbolt could take a cannon hit through the cylinder row and still bring its pilot home. One returned to base with half its tail missing and oil pressure at 0, the engine still firing on 12 cylinders. By mid-1943, bomber losses on deep raids remained catastrophic. Schweinfurt and Regensburg became bywords for disaster. P-47s could only escort bombers as far as Antwerp before fuel ran low. But within that radius, they changed the odds. The Luftwaffe's Bf-109G and FW-190A were optimized for climb and roll, not for surviving 8.50 caliber Browning M2s firing 120 rounds per second. German formation tactics began to collapse. Over the Channel, Thunderbolt pilots learned to dive from 9,000 MOs, $30,000 FT, through $1,000 met of cloud, hit 800 km H, and pull out so hard that rivets snapped. Compressibility flutter bent wingtips and peeled paint, but no aircraft failed structurally. The airframe was too strong. Zemke called it an armored anvil that outruns hammers. By the end of 1943, the 56th Group alone had claimed more than 250 kills. The Luftwaffe began calling the Thunderbolt der Sturmbach, the battering ram. Its sheer survivability forced German pilots to expend more ammunition and risk closer attacks where 50 caliber return fire was lethal. The balance of the air war was beginning to shift, one sortie at a time. By the time winter arrived, the P-47 was no longer an experiment. It was the face of American air power, brutal, fast, and impossible to kill. In the frozen skies of northern France, that brutality was about to be tested for the first time in blood. January 1944. The sky above northern France had turned into a factory of contrails and fire. The 8th Air Force was pushing daylight raids deeper into the Reich. Frankfurt, Brunswick, Kassel. Luftwaffe fighter groups scrambled in waves of 30 and 40 aircraft. For the first time, the Americans met them head-on with an escort that could take punishment and return it tenfold. The P-47C's first sustained combat over occupied Europe began on January 11th. 177 B-17s struck aircraft plants at Oschersleben and Halberstadt. 61 Thunderbolts from the 56th and 353rd Fighter Groups covered the withdrawal. At 10,000 meters, the air was too thin for mercy. Luftwaffe formations hit the bombers in coordinated attacks, Bf-109Gs from above, FW-190As from below. Within minutes, the sky was a grid of smoke and aluminum fragments. Captain Robert Johnson, 56th Fighter Group, logged what he later called the moment the R-2800 earned its name. His P-47 took 3 20mm hits through the tail and 1 through the oil cooler, the temperature gauge pegged at maximum, and the cockpit filled with smoke. Yet the engine never stopped. Johnson rolled inverted, dove through cloud, and flew 280 kilometers back to England on a single turbo stage. Ground crews counted 21 cannon holes. Not one vital line had ruptured. The data mattered more than the victory tallies. Combat analysis from SATE Fighter Command showed that the R-2800 could sustain 15 minutes of flight with total oil loss, something no inline engine on Earth could do. German pilots who expected Thunderbolts to trail smoke and die instead saw them keep climbing. They burn, but they do not fall, one JG-2 pilot wrote in his after-action log. That invulnerability changed tactics. P-47s began to hunt instead of escort. The heavy fighters used altitude as a weapon. Standard Luftwaffe procedure was to dive through bomber formations, fire, and climb away. Thunderbolt pilots reversed the geometry. They stayed high, waited for the dive, then counter-dived through the Germans, trading altitude for raw speed. At terminal velocity, the P-47 reached 800 km per Uhr, 500 miles. The FW-190A5 could not follow without shedding its wings. In February, Base Fighter Command authorized free hunt missions ahead of bomber streams. Major Zemke called it controlled chaos. Flights of 4 Thunderbolts ranging 100 kilometers into enemy airspace, slashing through airfields and rail yards, forcing the Luftwaffe to scramble early. The strategy worked. Intercepting the bombers now meant fighting through the escorts first. Operational statistics prove the shift. In September 1943, American bombers lost 1 aircraft for every 24 sorties. By March 1944, under Thunderbolt cover, the ratio had improved to 1 per 42. Kill-to-loss ratios for P-47 units averaged 4.6 to 1. The Luftwaffe's numerical advantage was dissolving. Pilots learned to trust the machine's mass. The P-47 could dive away from anything, but it could also take hits that destroyed lighter fighters. In one engagement over Chartres, Lieutenant Robert S. Johnson's aircraft absorbed 21mm shells from an FW-190 that closed to within 50 meters. The German pilot, frustrated that the Thunderbolt refused to die, pulled alongside, fired a salute, and broke off. Johnson limped home with hydraulic fluid streaming behind him. His ground crew later measured 5,000 holes in the fuselage. The engine still idled smoothly. At high altitude, the R-2800's turbo supercharger gave the Americans an invisible edge. German engines lost power above 7,600 meters, 25,000 FT. The Thunderbolt, with its twin-stage compressor and intercooler, maintained 800 horsepower up to 9,000 meters, 30,000 FT. German pilots who tried to escape by climbing found themselves caught by an aircraft twice their weight and somehow faster. After each mission, debrief logs filled with the same line. Enemy failed to break contact. Engine maintained boost. The phrase became shorthand for what the Luftwaffe feared most, a radial fighter that could fight on the vertical axis. By spring, the numbers were irrefutable. The 56th Fighter Group had claimed 348 victories with only 60 losses. Their pilots called themselves Zemke's Wolfpack. Even Luftwaffe radio intercepts used the nickname. When radar screens lit up over western France, controllers warned incoming squadrons. The wolves are hunting again. At the heart of every sortie was the same miracle of engineering, a cylinder wall 6 millimeters thick, holding back explosions hot enough to vaporize steel. The R-2800 turned that violence into altitude and altitude into dominance. Through 1944, engineers would push that violence even further, squeezing more air, more fuel, and more fury into an engine already at the edge of physics. In hangars from Boxted to Halesworth, the Thunderbolt was about to evolve again, this time into a machine the Luftwaffe would describe in one word: unstoppable. By mid-1944, American engineers had learned to weaponize precision. Every improvement to the P-47 came not from theory but from field reports, handwritten notes by pilots who had survived things no aircraft should survive. The R-2800 had already proven its strength. Now the challenge was refinement. The goal was brutal simplicity: more power, higher altitude, faster climb, same reliability. The first step was propeller redesign. The early narrow-blade Hamilton standard props could not absorb the Double Wasp's full torque. At takeoff, the propeller tips approached supersonic speed, reducing thrust and shaking the airframe. Tests at Wright Field led to the paddle blade propeller, broader and thicker, with variable pitch range extended to 55 degrees. On installation, takeoff run dropped by 200 meters, and climb rate jumped by 300 feet per minute, 1.5 memoirs. Pilots called it the lever that made gravity optional. Then came fuel. British chemical engineers had perfected 150-octane blends by mid-1944 using tryptane additives and ethyl lead concentrations unimaginable a year earlier. With new fuel came new power settings. Pratt & Whitney recalibrated manifold limits from 52 nhg to 70 nhg, 236 kPa. When mixed with water methanol injection, a 50-50 blend sprayed into the induction manifold to suppress detonation, the R-2800 could momentarily deliver 2,800 horsepower. The modification cost less than a single bomb, but turned every Thunderbolt into a 500 mm interceptor. The results arrived on the 5th of May, 1944, when 8th Air Force test flights recorded a P-47 D-22 reaching 805 km/h in level flight. The report's final line read, "No engine anomalies detected at full boost." That sentence signaled a new era. The next bottleneck was cooling. The turbo supercharger's heat output remained staggering. At climb power, exhaust gas temperatures exceeded 650 degree Celsius, roasting the cockpit. Republic engineers designed automatic cowl flaps linked to air temperature sensors, opening incrementally to maintain head temperatures near 210 degrees Celsius. It worked, but at a cost: drag. Zemke's pilots discovered that keeping the flaps half closed in combat gained 20 more at the expense of comfort. Most simply endured the heat. Every field unit became a laboratory. In Boxted, 56th Group Mechanics developed a cold boost mod, rerouting intercooler air directly into the carburetor at high altitude for an instant 200 horsepower surge. In Halesworth, crews replaced the standard turbos with experimental GE Type C units, polished smooth inside to reduce airflow turbulence. Those Halesworth specials climbed to $9,500, 31,000 FT, faster than any Allied fighter of the year. Statisticians at Wright Field compiled the data. Average time to climb from takeoff to 30,000 FT dropped from 18 minutes in the early P-47B to 12 minutes in the D-25 model. Dive recovery speeds improved to Mach 0.83 before control compression began. A German FW-190A8 entered compressibility at Mach 0.74. The Thunderbolt could chase through the sound barrier's edge and still pull out. Field modifications extended beyond performance. The heavy armor that once limited range now became a strength. Engineers fitted external drop tanks, 75-gallon, 284-liter, belly tanks, later 150-gallon, 568-liter, wing tanks, giving the Thunderbolt endurance up to 1,600 km/h. Escort lines pushed deeper into France. For the first time, bombers reached Berlin under American fighter cover. Even the cockpit evolved. The early framed canopy limited visibility during high G turns. In February 1944, Republic introduced the Bubble Top, a teardrop canopy molded from plexiglass, giving full 360-degree vision. It looked awkward, but transformed combat awareness. Pilots joked that it let them see who was about to die next. The numbers told the rest. In just 12 months, power climbed from 2,000 to 2,800 horsepower, speed from 430 to 500 mph, 692 to 805 km/h, and climbed from 2,500 to 3,400 min, 12.7 to 17.3 mmWs. No other frontline fighter in history had gained so much performance in so little time without changing its engine type. The R-2800 had reached its design limit and then exceeded it. But raw engineering was only half the story. On the ground, logistics kept that miracle alive. Each power plant required 400 man-hours to assemble and 17 hours to install. Pratt & Whitney factories in East Hartford, Kansas City, and Chicago produced 300 engines a day, coordinated through War Production Board schedules that calculated output to the minute. Replacement engines arrived in England 12 days after leaving the assembly line, crated in Cosmoline, ready to bolt in. For the Luftwaffe, this industrial rhythm was lethal. Every destroyed P-47 returned in numbers. Every damaged engine was replaced within hours. German mechanics rebuilt aircraft by hand. Americans replaced them like cartridges. The R-2800 had turned into not just a machine, but a supply chain. By June 1944, that chain would reach its peak. The invasion of Normandy was imminent, and the Thunderbolt was no longer a high-altitude escort. It was about to become a weapon of ground destruction. The engine built to chase Messerschmitts would soon learn to kill tanks, and in doing so would help turn the tide of a continent. June 6, 1944. Dawn broke gray over the English Channel. More than 5,000 ships stretched from horizon to horizon, and above them roared a sky owned by the R-2800. Nearly half the fighters covering Operation Overlord were Thunderbolts. Their pilots had trained for dogfights. That morning, they became artillery. The 56th, 78th, and 362nd Fighter Groups flew 150 sorties on D-Day alone. Their targets were not aircraft, but bridges, rail junctions, and armored convoys converging on Normandy. Each P-47 carried 10 5-inch HVAR rockets, or two 500-pound bombs. The same engine that once lifted a 7-ton fighter to 30,000 ft now hurled that weight downward at 400 knots through anti-aircraft fire. The Luftwaffe barely appeared. Fuel shortages and radar confusion left their airfields paralyzed. The few Bf-109s that rose to intercept met Thunderbolts diving at speeds beyond 480 mph, 772 km/h. A typical fight lasted less than 30 seconds. In one report, Lieutenant Francis Gabby Gabreski destroyed two FW-190s in a single pass and was gone before the German wingmen could roll to follow. The greater war was below. Allied tanks advancing from Omaha Beach reported that Thunderbolts seemed to appear whenever the Germans started to move. The fighters' 8 50-caliber guns could shred trucks, locomotives, and half-tracks in seconds. In the first week after D-Day, P-47s destroyed more than 800 vehicles and 200 locomotives across northern France. What made the aircraft uniquely effective was its survivability. Ground fire that would tear apart a Mustang or a Spitfire often left the Thunderbolt scarred but flying. Armor around the cockpit and oil cooler weighed nearly 150 kilograms. Self-sealing fuel tanks held 1,000 liters of high-octane gasoline and could absorb direct hits without explosion. One Thunderbolt returned from Falaise with its right horizontal stabilizer completely shot away, still producing enough lift to reach base. Mechanics painted a single line on the fuselage: "Engine never quit." The R-2800's turbo supercharger was equally relentless. Flying low-level attack runs at 1,500 mph, pilots throttled up to emergency power, 70 NHG boost with water injection. The roar of the exhaust turbines echoed through the Bocage valleys like rolling thunder, giving the aircraft its battlefield nickname, Juggernaut. German infantry shortened it to Der Jug. The name spread faster than radio signals. By July, Luftwaffe intelligence was circulating new orders. Avoid single combat with P-47s below $6,000 MEM. The radio fighters' acceleration in dive and climb made disengagement impossible. German ace Günter Rall later wrote, "They came from above, they came from below, and they never broke apart. You shot at one and another arrived." While the Luftwaffe dwindled, the Thunderbolt's mission evolved. Escort duties shifted to the longer-range P-51 Mustangs. The P-47 became a hammer for the advancing armies. Pilots modified their own armament, strapping on 1,000-pound bombs or clusters of 4.5-inch rockets. With the R-2800 at war emergency power, each sortie carried as much destructive force as a light bomber. On August 7th, 1944, near Mortain, 2,000 German tanks and vehicles massed for a counterattack. Weather grounded most Allied bombers, but the Thunderbolts flew anyway. For 9 hours, flights of 4 attacked through fog and smoke, guided by radio calls from spotters on the ground. By evening, German armored divisions lay burning across 12 kilometers of road. Army reports credited the P-47s with destroying or disabling 120 tanks in a single day. The scale of destruction was industrial. Republic Aviation's production line at Farmingdale delivered 1 new aircraft every 75 minutes. Pratt and Whitney engines arrived faster than airframes. In August, 8th and 9th Air Forces operated 2,000 Thunderbolts simultaneously, the largest single-type fighter fleet in history. German morale collapsed under the combined pressure of relentless air power and ground losses. Radio intercepts recorded phrases like the Big American Radial and the Unkillable Silver One. On the Eastern Front, Soviet pilots flying Lend-Lease P-47s repeated the legend. One report from the 255th Fighter Regiment described a Thunderbolt returning from a mission with 2 cylinders shot out, still generating power on 16. By autumn, the Luftwaffe had lost the war in the air. Strategic bombing continued unopposed over the Reich. German aircraft production dropped by half under constant Thunderbolt strikes on rail hubs and oil depots. The air superiority that had begun in failure over Bremen was complete. In less than 18 months, a machine once dismissed as overweight and obsolete had broken the back of Europe's most advanced air force. But the R-2800's reach would not stop in France. Its power would ignite engines across oceans and continents, defining the shape of Allied victory itself. By the autumn of 1944, the R-2800 had become the beating heart of Allied aviation. From the Arctic convoys to the islands of the Pacific, its roar marked the rhythm of victory. What began as a desperate experiment in overpowered engineering had evolved into the most produced, most adaptable aircraft engine of the war. Factories across the United States turned night into day to feed the demand. Pratt & Whitney's main plant in East Hartford ran 3 shifts, 7 days a week. Satellite facilities in Kansas City and Chicago duplicated every jig, every fixture, every test cell. By September, one completed R-2800 left an assembly line every 6 minutes. In total, more than 125,000 units would be built before the war ended, enough power to lift 1 million tons of aircraft. Its reach extended far beyond the Thunderbolt. The same Double Wasp powered the Navy's F-6F Hellcat, the carrier fighter that crushed Japanese air power in 1944 with a kill ratio of 19-1. It drove the F-4U Corsair, whose inverted gull wings became the terror of the South Pacific. It pulled twin-engined B-26 Marauders across Europe and pushed PBY Catalinas over endless ocean. Wherever Allied aircraft needed power, the R-2800 answered. Each variant adapted to its environment. The 8W model with water injection equipped the P-47D. The 10W became the Hellcat's heart. The 18W served in the Corsair and B-26. Pratt engineers learned to modify compressors for altitude, change reduction gears for propeller types, so and swap magnetos between models without halting production. The result was a standardization effort unprecedented in a wartime industry, 90% of components interchangeable across more than a dozen aircraft types. The War Production Board tracked everything. In 1943, it took 18,000 man-hours to produce one B-17 bomber. By 1944, a single R-2800 engine required just 1,100 hours. Efficiency had become a weapon. Every engine left the plant in a wooden crate lined with wax paper and nitrogen-filled bags, accompanied by a logbook of 212 inspection signatures. None were rejected for mechanical failure. Logistics followed the same precision. Crates traveled by rail to New York, loaded on Liberty ships, and reached Britain in under 2 weeks. Engines destined for the Pacific went west through San Francisco and Pearl Harbor, arriving in Australia within 30 days. In the field, mechanics could swap an entire R-2800 in 5 hours. The Luftwaffe's repair time for a DB-605 averaged 3 days. The difference was not technology, but tempo. That tempo reshaped the Allied air strategy. With the P-47 dominating Europe, the Navy's Hellcats and Corsairs carried the Double Wasp into the Pacific's final crucible. In the Marianas, Philippine Sea, and Okinawa campaigns, R-2800-powered aircraft destroyed over 7,000 Japanese planes. The radial's thick cylinder walls tolerated the humid salt air that corroded liquid-cooled engines. Mechanics cleaned them with rags and oil instead of replacing radiators. Pilots trusted them the way infantry trusted rifles. They simply worked. Combat data from the Pacific underscored what Europe had already proven. Average flight hours before major overhaul, 430. Mean time between failure, 52 hours. Engine-related aborts in combat, less than 0.3%. The R-2800 was not just powerful, it was statistically invincible. When victory became inevitable, the War Department's technical intelligence teams began cataloging what had made it possible. Among the most cited machines were not the atomic bomb or the radar array, but the Double Wasp. Its technical summary filled 46 pages. 18 cylinders, 6.8-inch bore, 6.75-inch stroke, 2,804 cubic inches displacement, compression ratio 6.65.1, takeoff power 2,800 horsepower at 2,700 RPM. Numbers that now defined air supremacy. Even after Germany's surrender, the engine kept evolving. The P-47M introduced higher boost and thinner wings for 470 memorampilus intercepts against V-1 rockets. The P-47N, with extended wings and massive fuel tanks, escorted B-29's 2,000-kilometer cars across the Pacific to Japan. On those missions, Thunderbolts returned on cylinders, leaking oil and manifolds, scorched black but always under power. In the post-war years, Pratt & Whitney converted the R-2800 for civilian transports, the Douglas DC-6, Martin 404, Convair 340. The same pistons that had torn across Europe now carried passengers in silence. The engine outlived the factories that built it. Many of those engines still run today. By the time the last Thunderbolt rolled off the line in 1945, the Double Wasp had done more than win air battles. It had defined an era, an industrial symphony of noise, heat, and precision that turned engineering into strategy and horsepower into history. The war would soon end, but one truth would remain. In the sky above Europe and the Pacific, victory had sounded like the thrum of 18 cylinders, firing in perfect, merciless rhythm. By the final months of 1945, the Thunderbolt had become both symbol and relic, the last of the piston giants standing on the threshold of the jet age. Its vast wings, its circular nose, its screaming turbocharger had carried America from survival to dominance. When its pilots taxied back to their dispersal bays after victory flights over a broken Europe, most simply shut down the engines and listened to silence for the first time in years. That silence was earned. The R-2800 had turned numbers into survival. Its torque curve was mathematics made audible. It carried a 7-ton airframe through dives that shredded rivals, through anti-aircraft fire that vaporized fuel and coolant lines, through skies where nothing else could endure. In every test log and after-action report, one phrase repeated until it became a creed. Engine held, aircraft returned. The machine was indifferent to glory. It did not know it had changed the balance of war, but the men who flew it understood. They trusted the weight, the power, the sound that began as a growl and rose to a full metallic howl. They learned that speed was not just a measure of movement, but of faith. Faith in engineers they would never meet, in factory workers who riveted, welded, and inspected through endless nights, and in the unseen arithmetic of combustion that kept them alive. When the Luftwaffe collapsed, it did so under an avalanche of American power built from that faith. The R-2800 made industrial might audible, 2,800 horsepower at a time. Its cylinders consumed 1,000 liters of fuel each hour, but they also consumed doubt. Every rotation of its crankshaft was a promise that the Allies could outlast, outbuild, and outfly an empire built on precision and fear. Historians would later call it the engine that won 2 oceans. In truth, it did something quieter and deeper. It erased the idea that complexity and reliability were enemies. It proved that a machine born from chaos could become order, that a system built on risk could define endurance. Even as jet engines replaced it, no pilot who had heard that radial thunder ever forgot its rhythm. After the war, thousands of Thunderbolts were melted into scrap, their aluminum skins recycled into cars and bridges. But the engines, many were preserved, started again, and still run today, decades later, with the same unbroken pulse. Their sound belongs to history now, but their lesson belongs to every age that builds under pressure. Perfection is not achieved by avoiding failure, but by surviving it. For every Thunderbolt that roared home on one engine, men on the ground had built it to do exactly that. And for every flight that returned through smoke and flame, the numbers proved what courage alone could not, that faith in engineering could turn impossible weight into flight, and flight into victory. If stories like this help you see the war, not just through the eyes of those who fought, but through the minds of those who built, remember to keep these declassified histories alive. If you found meaning in this story, in the hands that shaped steel and the minds that refused to quit, consider subscribing. It helps preserve the legacy of the machines and the people who turned the tide of history, one revolution at a time.